If we look at our first linear pattern, we have our input values here and our output values on the right side. If we compare that to our arithmetic sequence, we use braces instead. The first number is considered a sub 1. It means it's the first number in the sequence. That's what this 1 is for. This 7 would be a sub 2 and a sub 3. And if we compare a sub 1 to this value right here, you can see there's the 1. This is the 1 on a sub 1, the first number in the sequence, and then this would be the value itself, the 4. Now if we're looking at the pattern, all arithmetic or linear patterns have a number, a constant that's being added. So if we look at 4 to 7, we can see it's a plus 3. Now if the number's a decimal or you can't think of the number, we can always go backwards. If it's adding forward, then it's subtracting backwards. So if I take two numbers like 10 and 7, and I subtract 7 from 10, take a term number and subtract the one that came before, that's going to give you your common difference. This is the number that was being added to make the arithmetic pattern. In terms of a graph, we're going to graph this one, and I'm going to graph the linear. So -1 went with -2, 0 is up here at 1, 1 goes with 4, and 2 goes with 7. I'm not going to fit the last one, but you can see that it's going to form a line. If my graph would have been drawn a little bit better, that would have been a nice straight line. So arithmetic and linear equations, when you look at the graph, it's going to be a straight line. For the equation, we were given for the explicit a sub n equals a sub 1 plus d times n minus 1. So if we use this as our pattern, a sub 1 is the first number in the sequence. We already said that that was a 4. D is the common difference. We found that in the arithmetic side, that was a 3, the number being added each time. And then we can multiply by n minus 1. Now on the left, if it's a sequence, I might have a sub n. If it's an equation, I might see a y, and the n might be an x instead. If we want to test our equation and make sure it works, if we take, I'm going to take 10, you can see that 10 is the 1, 2, third term, so a sub 3. If I plug a 3 in for my variable, meaning I'm going to change that n into a 3, I can type all of this in my calculator, and it's going to give me a 10. If I didn't have a calculator and I wanted to do it with order of operations, I would subtract the 3 and the 1 first, because parentheses come first, so 3 minus 1 is 2. I would then multiply 4 plus 3 times 2 is 6, and then 4 plus 6 would give me the 10. I would always suggest you check your equation before you decide that you're finished. The next function is an exponential. You can see that we have the same notation. I have my x and y on the left. And if we talk about a geometric sequence, you can see that the numbers are lined up in more of a sequence with commas in between. 1, 5, again, the 1 value on the x is like your a sub 1 or your first term. Now this pattern has a multiplication constant that's being multiplied. So multiplying 5 times 2 will get us 10. If I didn't know that number, I could again take two numbers that are consecutive, and I would divide one by the term that came before it. So 20 divided by 10 will also give you 2. That's called the common ratio. In terms of a graph, I have 0 with 2.5, which is almost down here because I counted by tens. Each line is 10. I have 1 with 5. That's maybe a little bit higher. 2 goes with 10. Okay, now we got to that first line. 3 goes with 20. And then 4 with 40. So please ignore that. That was an accident. There's your curve. So an exponential looks kind of like a curved L shape or a J. It'll have a slow side, so this side actually will get lower and lower and get very, very close to 0. But there's not much change in the y values. And then it'll have a faster side, this side, where those y values are just shooting up towards infinity very, very quickly. For the equation for these, if we use our geometric, it says that we take the first term, multiply by the common ratio, and it'll have an exponent of n minus 1. So if we take the 5 was our first number in the sequence, we multiply by that common ratio of 2, the number being multiplied, and then raise it to a power of n minus 1. If we want to test this, I'm going to use the 20. That was our third number in our sequence. So if I plug a 3 into our equation, I should get a 20. Now with this order of operations, I would do the exponent first because there's implied grouping symbols. So 3 minus 1 will give us 2. We do multiplication next, or exponent, so 2 times 2, or 2 raised to the power of 2 is 4, and then 5 times 4 would give us that 20. Our quadratics, if we take the difference between 8 and 5, which I would think to myself 8 minus 5 is 3, and we take the difference here, we get 5, and if we take the difference here, we get 7. 20 minus 13 is 7, and we get 9. You'll see that they don't have a common difference. So what we need to do is we need to check for a second common difference. So if I take the difference between those differences, so I'm thinking to myself 5 minus 3 is 2, and I do the same with 7 and 5. 7 minus 5 is 2, and 7 minus 9 is 2. They have a common second difference. That's how we know it's a quadratic pattern. I'm going to talk about the graph first. So the graph of this would be those parabolas from last year. So 0, 5, 1, 8, 2 goes with 13, a little bit past 10, 3 goes with 20, and it kind of curves up like this. Now, I didn't give you any negatives, but on a quadratic, the left side's going to be symmetric. The reason that we don't see a lot of negatives in this section is because we have these visual patterns, and showing negative dots is a little bit more difficult. But you're going to get a nice parabola from this quadratic function. Okay, we're going to talk about the visual pattern to talk about the equation. So with the visual, you want to break it into shapes that you know. If you look at the 3 figures that I have, figure 1, figure 2, and figure 3, it's kind of a square here. This is also a square because it has sides that are the same length, a 3 by 3. This one would also be a square, it's a 4 by 4. And then you have these, I'm going to call them corners. So if we break it into pieces, we need to get the area of the square and add it to those 4 corners. So for the area of the square, I'm looking at figure 1. It's a 2 by 2 square. It has 2 dots across and 2 dots down. Figure 2 is a 3 by 3, and figure 3 is a 4 by 4. And then I'm thinking to myself, how do I get from plugging in this figure number into my variable and get out that 4 that I want for the side length? So I'm noticing that it's always 1 more. The figure number plus 1 gives me that side length. So I'm going to use n for the figure number and plus 1. That's the length of the side of my square. Now, since the other side is also the same, I'm going to multiply that by n plus 1. Or I could have written it as n plus 1 to the power of 2, showing that it's multiplied by itself. With the corners, it looks like there's always 4 corners. As the picture grows, those don't change. So that's going to stay a constant, plus 4. So again, the n plus 1 times n plus 1 gives you the area of the square, and then the plus 4 gives you the 4 corners. We're going to test our equation, and I'm going to use figure 2 this time. So the 2 is the figure number. I'm going to plug a 2 in for my n's. And again, I just used this equation. I replaced my n's with 2's. Order of operations, I'm going to get the grouping symbols out of the way. So 2 plus 1 is a 3. 2 plus 1, I have another 3. And then plus 4. 3 times 3 is 9. That 9, again, is these 9 dots there in the middle. And then plus our 4 corners. And we got our 13 dots.